Hey guys, hope you guys are doing really well and having a great weekend. Today I will be going over the IR evaluation section as I wasn't able to finish during my discussion section, so hopefully this will be very helpful. So let's get started. So essentially for IR evaluation, you want to be answering the question of how well your system works, okay? So given multiple systems, system A, system B, how do you assess whether system A is better or system B is better given different queries that are retrieved, right? Now, we previously looked at precision and recall, and just as a recap, precision is essentially true positives over the true positives plus the false positives, and then recall is the true positives over the true positives plus false negatives. So this is definitely quintessential, and you should know it. And we've also looked at how you can use or calculate precision and recall at a macro and micro level. Okay, so understanding that is also pretty good. We also looked into what a recall and precision plot is, and essentially it's a way to at a snapshot evaluate different systems using the graph. So you have on the y-axis the precision, and then on the x-axis the recall, and so it's a detailed picture. So you're able to identify, whether there's any different behaviors between the two systems, but essentially you would want to average it towards the end. In order to average it, you require all the precision and recall values, but sometimes that is not always possible, and that's why we use something called interpolation. So interpolation is a way of what we call an optimistic estimation or optimistic interpolation. So in a way, it's an estimating of precision at a recall level. And how you do that is essentially, let's say we look at the blue curve here, okay? Well, this is one system. We're looking at this curve, okay? So let's say you want to, so essentially the way you estimate precision at a level recall, you look to the right and see the highest precision at that point. So if your recall level is at 20%, 0.2, and you want to measure the precision at this point, right? Well, we can see that it's about what, 50%, okay? So, but instead of 50% for that recall, we will look to the right and look at the highest precision, okay? So if you look to the right, and the highest precision at that point, okay, is about what, 66%? So you're going to use that for your entire range. So precision at 0.2 is going to be 50%, and then precision at, let's say, 0.25 is also going to be 50% because if you look at 0.25 here, the highest value that we have here is 0.5. So it's all going to fall under this range, okay? All the way up to 0.4 until we get to here, okay? And this is what we call an optimistic interpolation. So anything up to the recall of, like say, 33% will have a precision value of 50% and so on. So once you have this function from the interpolation, you can take the average of the curves and you get what we call a recall precision curve as such. Okay, so this is the average of all the curves. Now, in a way, as I mentioned, it's also a snapshot, and you'll be able to identify, how well your system is performing in terms of precision and recall, and we'll go into detail as to how you can do it exactly. But just as more content, this is a precision recall curve of averaged over 50 queries. Normally, you'd have thousands and thousands of queries, and you can actually determine, depending on the different system you have, whether the performance yields high precision or high recall, depending on the user base. And you can also make some meaningful system comparisons. So in this instance, we can see that A is worse than B if recall is more important, right? But you can also see that A always performs better than C as an overall because it dominates on all recall levels. So just being able to average over different systems through this curve, you'll be able to gain a more insightful snapshot of how well these systems are performing. So we looked over different ways of doing this in class. So this is pretty straightforward. And then for the just comparing again for the comparison of systems, we know that in the top right corner, this is the gold standard. So this is where you have perfect precision and perfect recall, and you can see in this other example that for a system that is not stemming and then a system that is stemming in blue, we can determine that the system that is performing stemming performs much better as it's much closer to the top right corner. Okay. We also discussed in class mean reciprocal rank. So let's say you consider a rank position at K of first relevant documents. So the reciprocal rank score is essentially just 1 over K. And then the mean reciprocal rank is just the mean of the reciprocal ranks across multiple queries. And then now we're going to an exercise of how to do this. Let's suppose you have built an information retrieval system that retrieves the most relevant documents for a user search query. Okay, so for query 1, the ranked lists are D2, D1, D4, and D3, and the relevant documents are D2 and D3. Okay, for query 2, on the other hand, the ranked list is D3, D1, D4, D2, and the relevant documents is D1 and D2. Now let's say you're given the question, calculate the mean reciprocal rank for these two queries based on the given rank list and relevant documents, okay, given this information. Now, I would say pause the video now and try to determine how to do this. Otherwise, if you have the solution, you have an idea, I'd say you can just skip through. But let's just take this with us. Okay. So essentially, oh, never mind. Okay. There we go. So essentially, in order to calculate the MRR, first you're going to have to compute the reciprocal rank. So for query 1, we're given a ranked list of D2, D1, D4, and D3, D2 and D3 for the relevant documents. So the first relevant document in the ranked list is D2. Now D2 in the ranked list is at position 1, right? So since it's at position 1, the RR essentially, as we know, it's 1 over K, right? So it's just going to be 1 over 1, which is 1. Okay, so the RR for 1 is just 1. Now for query 2, we're given the rank list, we're given the relevant documents, okay? The first relevant document in the rank list is D1. Now D1 is at position 2 in the rank list, okay? So since K is 2, it's simply going to be 1 over 2. So RR for query 2 is going to be 0.5. Okay, so we have R for 1, R for 2. Okay. Now, the first relevant document in the rank list, as you can see, we have, just to reiterate, we have 1 and 0.5. Okay, so if you want to calculate the MRR, essentially you average the RR values. So MRR is just RR1 plus RR2 over 2. Okay, so we have two values. So in this instance, MRR is just going to be 0.75. So we can conclude that the mean reciprocal rank for these two queries is 0.75. Cool. Now in class, we also looked at, map and R precision. So R precision is essentially the precision value at the rth rank in the retrieved results for a query, and R is essentially the number of relevant documents in that situation. And we're able to do this by getting the number of retrieved relevant documents at R over the total number of relevant documents. Okay. Now for mean average precision, or MAP, for each rank K, where K is the rank at which a relevant document is retrieved, you calculate the precision at K and take the average of those values. That's simple. We also discussed Kendall-Tau. Now, Kendall-Tau is another way of comparing the ranks. So you're given pairs, right? You're given an order of, A, B, C, D, right? The pairs would essentially be AB, AC, AD, BC, BD, CD, okay? And you're given essentially two pairs, normally one for the ranking generated by your system, and then a perfect ranking. And so the Kendall-Tau formula is x minus y over x plus y, where x is the number of agreements, so the same pairs between a ranking generated by your system and a perfect ranking, and this is often hand-determined, you could, and y is the number of disagreements in the same scenario rather than the agreements. Okay, so once you're able to get x and y, you just plug it into the formula, and that'll give you the Kendall-Tau distance given two systems. And it's a way of comparing the two systems, how close they are in terms of ranking. Okay. Now, precision at K, we often use this for mainly use this, for ranked R systems only. And then R precision is the same as the precision at the number of relevant document. So if you want to look at the precision at k. So precision at 1 is going to be 1 over 1 because you have one document that is relevant over one document in total. And then for this instance, we're at ranking 3, it's going to be 2 over 3 precision. So precision at 3 because you have 2 relevant documents over the total amount of documents. So 1, 2, 3. And you continue this to, let's say, precision at k at 5. And in that instance, it would be 3 over 5, 3 over 5 because you have 3 relevant documents up to that point and 5 documents in total. So just 3 over 5. Okay. Now that was just precision at k. Average precision is just each relevant document ranked at ki, and you get the precision at ki, and you average over the relevant documents index I. So the mean average precision is just the average over queries, okay? And the average, let's say, we have the values of 1 over 1 for precision at k here, 2 over 3 at precision at k at 3, and then 3 over 5 for precision k at 5. So the average precision for k at 5 is just going to be this plus this, so the sum of these up to that point, divided by 3, because you have 3 instances that are relevant. Okay. Now, mean average precision is a metric used to evaluate the effectiveness of an information retrieval system by averaging the precision scores of multiple queries. Okay, so the formula for mean average precision, it can be broken down into 2 parts. So you calculate the average precision for each query, as we did before. Okay, and then you average those values across all queries. So if you want to calculate the average precision, just as a reminder, it's sum of precision at k times the relevance k, over the total number of relevant documents at the query. So pk essentially is the precision around k. Rel k is the indicator function equaling 1. So in this instance, it's abstracted because when it's relevant, it's times 1. So it's simplified. So it's the function equaling 1 if the document at rank k is relevant, and then 0 otherwise. And then to calculate the mean average precision by averaging AP values all over the queries. So map is essentially the sum of AP of all queries over the total number of queries. And this is very useful because, so why do we care about this, right? This is very useful because the system in itself, this takes into account both the precision and recall of an RS system, giving a single value for evaluating the system's overall performance. So quite essential. Now let's go into an exercise of calculating, using precision and recall to evaluate a system. So assume you have an RR system for which query 1 returns the following ranked documents. Okay, assume that for query 1 the relevant documents, document IDs are A, C, F, and I. Here in bold. Now I want you guys to calculate the precision at 9, the average precision at 6, and then the interpolated precision for R is 0.3. Now, I recommend just pausing this video and then trying to do the exercises. Otherwise, I'll be going through the solutions now. So, just to reiterate and to break it down to words, precision is the total number of retrieved documents that are relevant over the total number of documents that are retrieved. In our instance, we have, at precision at 9, we have 9 documents that are retrieved in total. And then out of the 9, 4 of them are relevant. So that's just going to be 4 over 9. And just to reiterate, for the exam, it's okay to leave it at a fraction, or if we do specify, we want a certain amount of decimal places. But if it's not specified, you can leave it as a fraction, or just up to like 3 decimal places is sufficient. Now, for the second part of the question, you have calculating the average precision at 6. Now, average precision at 6, which is the average of the precision values at the ranks of relevant documents within the top 6. So essentially, if you look at the relevant documents at top 6, this is only A, C, and F, because we stop at 6. And then you just calculate the precision at each rank. So at rank 1, you have 1 document, 1 is relevant, there's just 1, 2 over 3, 3 over 6. Okay. And we're not, so this is it, because if we ask for the mean average precision, then you can take the average of all of these, okay? But in this instance, we're only asking for the average precision. Now, part 3 of the question, we're asking the interpolated precision for R is 0.3. So you can break this down into different steps. For step 1, you calculate the precision and recall at each rank. So given this table here, you want to be calculating the precision and recall. Okay, so just as a reminder, precision at a given rank is the number of relevant documents up to the rank divided by the rank. Okay, and recall at the given rank is the number of relevant documents up to the rank over the total number of relevant documents. So as shown here, these two columns. Okay. Now, once you have precision and recall values, step 2 is to calculate the interpolated precision of those values. So the interpolated precision at a specific recall level is the highest precision found for any recall level greater than or equal to the given recall level. So as you can see, we have the intervals here, 0 to 1, okay? And then for each instance, the interpolated precision at that recall level is the highest precision found for any recall level greater than or equal to the given recall level. So essentially, given these values, you'll be able to determine that. Now, once you've done that, you can locate the interpolated precision at R is 0.3 in this instance, and then the interpolated precision for R is 0.3, it will be 0.667. Okay, pretty straightforward. Now, exercise 3. Now, let's assume an IR system for which query 1 returns the following ranked documents, and let's assume for query 1 the following document IDs are relevant. So we have, let's say for query 1 is yellow, and then for query 2 is purple. Okay, so for query 1, A, C, and F, A, C, F, I are relevant, and then for query 2, E, H, A, and J, and G. Yeah, so E, H, A, J, and G are relevant. Okay. Now, considering query 1 and query 2's results, compute the following: the mean average precision at 8. Okay. So just pause this video and then try to figure it out before looking at the solutions. So essentially, to compute the mean average precision at 8, we are first going to look, we first need to compute the average precision for each query at rank 8, okay, because we're going to take the average of the two. And then you take the mean of those average precision values, all right? So for query 1, you have the relevant documents, A, C, F, and then the results up to rank 8 is just A, B, C, D, E, F, G, H. And the relevant documents retrieved are ACF, right? See, we're not using I because it's not part of the up to rank 8. So the precision at each relevant rank, so at rank A at rank 1, is just precision 1. That's rank 3, 2/3. At rank 6, 3/6, okay? And as a reminder, the relevant document I is not retrieved within the top 8 ranks, hence it does not contribute to the average precision for query 1, okay? So the average precision for query 1 is just going to be 1 plus 0.67 plus 0.5 over 3, because it's the total number of relevant documents. So yeah, let's go 2.17 over 3, which will be 0.7233. And you repeat that for query 2, okay? So I won't be going over this in such detail, but it's the same steps. So given the relevant document IDs and then the results up to rank 8, you find which documents are retrieved to that point. Then you calculate the precisions at each rank. So for 3, 4, 5, 7, you get these precision values, and then you just take the average of those precision values given over the total relevant documents. So it'll be 2/5. Okay. Now, once you have that, right, you can calculate the mean average precision at 8. So in that instance, it's just going to be the average precision for query 1 plus average query for precision query 2 over 2, because we have two total average precisions. And so that's just going to be this. So we get 0.56. Okay. Hopefully this is straightforward. Yeah, sounds good. Moving on. Exercise 4. All right. Assume an ideal ranking for a particular query shown in the leftmost table. So you have the ideal ranking, say, in yellow, and then you have the candidate ranking in purple. Okay. Compute the following: the Kendall tau distance, right? So as a reminder, Kendall tile distance was the agreements of minus the disagreements over the agreements plus the disagreements, right? And in order to do this, you're going to have to find the pairs for each. So then again, once again, sorry, try to solve this without looking at the solution. And then if you have any questions, please just put on Piazza. But otherwise, I'm just going to be moving on to the solution. So to calculate the Kendall tile distance, we first need to find the number of agreements, x, right? Number agreement, sorry, number agreement x, and then the disagreements of y between the two rankings. So we have the ideal ranking and candidate ranking. So first, you want to list out all the pairs of documents that appear in both rankings. So note that H and J are not present in the ideal ranking, and G is also not present in the candidate ranking. So G is not present here, and H and J are not present here either, given that it's here, here, and here. So that they will not be considered in the pair comparison. So if you list out all the comparisons, this is what you get. Okay. Now, given that, we can count the number of agreements and disagreements. So essentially, given the pairs that you generated, you'll be able to compare between the two rankings. So for AB, that's a disagreement, AD, that's an agreement, and so on and so forth for each pair that you generated before. So once you've done that, you'll be able to have the number for the agreements and then the disagreements, and then you just plug it into the formula. So it's a 6 minus 9 over 6 plus 9, which is minus 3 over 15. So we get a Kendall tile distance of negative 0.2. So yeah, you can have negative values for the Kendall tile distance. And the distance between the ideal and candidate ranking is essentially negative 0.2. So not great at all. Okay. Okay, hopefully you guys are following. Please, like, if you guys are watching this in one go, try to take some breaks in between, stretch, drink some water, I don't know. But yeah, it'll be much better in terms of learning. But otherwise, let's move on to the last exercises. So we also looked in class of discounted cumulative gain. So, normally when we look at um, documents that are relevant or non-relevant, we look at a binary system where 0 is like non-relevant and then 1 is relevant. But what if you wanted to have a somewhat non-binary relevance judgment? So something more fluid, so 0.1 relevancy, 0.8 relevancy, 0.9 relevancy. In essence, this is what we do in order to do. So we use discounted cumulative gain. And then relevance in the form is not a label. Yeah, sorry. Relevant in the form is the label, not produced by the system. And essentially, it puts more importance to high-ranked documents, and then it's degraded to cumulative gain without this discounted term. So essentially, you'd have a table as such, and then the discounted gain formula is here, right? So you have the relevant at position 1 plus the sum of all the relevancies, like gain, right, over the log base 2 of I. Yeah. Now, the normalized DCG is essentially when you take the discounted cumulative gain over the ideal ranking, so ideal discounted cumulative gain. And this can be used to compare across all queries. So that's why you have to normalize it. Okay. So for exercise 5, let's assume the following result for the RS system for query Q, okay, and I is the ranking, and Ri is the relevant score for the set of 0, 1, and 2. Calculate the normalized discounted cumulative gain. So I'll give you guys a couple minutes so you guys can figure this out, and then we can move forward. So essentially, what you want to do is the discounted cumulative gain of ground truth is the ideal DCG. So if you look at the table here, right? We're given the set 0, 1, and 2, so we care about these values in each. And so for the discounted cumulative gain at the ground truth, it's just 2, because that's the relevancy that we have. 2 plus, and then you can take the sum, right, as such. You'd be taking the sum of each of each value here. So here you have 2 over log base 2 of 2, and then plus 1 over log base 2 of 3, because we're at 3, and then plus log base 2 at 4 over 0 because the value is 0. Okay, and that'll give you 4.6309. And then since we want the normalized discounted gain, we're going to have to calculate the discounted cumulative gain for RF1 and RF2. And then you follow the same pattern. You input these values given the position that they have. So 2 plus so you have 2 plus 2 over log base 2 of 2, 0, and 1, and then here you have the rankings of 3 and 4, so that gives you 4.5, sorry. And then you repeat that for RF is 2, and then you give 4.619. And essentially, the normalized discounted gain, as I mentioned before, is just the discounted cumulative gain of n over the ideal discounted cumulative gain. Okay, so the system 2 has precision at 3 at 1, but has a lower uh, normalized discounted gain. So here, as you can see, we have the value for the ground truth, right? DCG at ground truth is 4.6, and we divide over DCG at RF1 and RF2, and you can see that RF1 has a higher value. Yeah, that's pretty much it. Hopefully, you guys, this was pretty helpful. I know I somewhat went faster in some sections, but hopefully, this was like a holistic overview of the different exercises that are required for our evaluation. Please don't hesitate to post questions on Piazza if anything's unclear on these exercises. But yeah, I hope you guys the revision goes well and you guys have a great weekend. Thank you.